Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. And boy, have I got a paper about manufacturing today. It's all about incremental sheet forming. More on that in a moment. This paper comes to us from John Weeks and Aaron Stebner of Georgia Tech. Let's dive into it. Okay, incremental sheet forming falls in this broader camp of things called metamorphic manufacturing. It says here this is a manufacturing approach that uses numerically controlled incremental deformation in order to achieve complex shapes and tailored local properties. So instead of casting some complex shape where everything in that is going to have more or less the same properties, if you deform that material to come up with a net shape, then this spot over here might have a different set of properties than somewhere over here. You can actually design this to have locally relevant properties. So it says incremental sheet forming is one that does this. It uses numerical control to incrementally deform the material into some final shape. And there's different ways to do this, right? There's single point, but also variations like double-sided and on, okay? Whichever process you're using, you're going to want to model how when you deform the material, what happens to the microstructure. So you're going to be deforming a material and modifying the properties near the deformation. This means that we have different length scales of interest. For example, the grain evolution behavior is going to happen at a very micro scale, but the deformation is going to be a macroscopic deformation. And the way to merge these two length scales is typically done via crystal plasticity, where you can actually model the individual grain response, tracking individual grains if you want within some representative volume element. And this has been done before. For example, Ismail-Pour showed that you could apply this to incremental forming of YLD 2004 18P. Here's that paper where you can see they were actually modeling the deformation of a 7075O aluminum sheet undergoing single point incremental forming using crystal plasticity and 3D RVE. And the problem with that is that these sort of hierarchical methods are just really, really slow, right? They require a lot of effort and expertise, and ultimately they are slow. But the innovation that these authors are putting forward is the possibility of using machine learning surrogates instead of those. And they're not the first people to consider this either, right? There's been a number of papers primarily using recurrent neural network architectures. And that makes sense because a recurrent neural network saves some information about the previous state when it captures the next state. So in incremental forming, that's going to be really important. The one that they actually used here comes from Bonatti and Moore. This is a recurrent neural network they call linear minimal state cell, which is able to capture self-consistency in this process using the history dependence. All right, so they're essentially going to use a machine learning model to replace the crystal plasticity model. There's actually two different ways that they implement this. You can read about them in their paper, right? But basically they have MSNR, which uses it once, and this MS-EVPSC, which actually uses two different machine learning iterations of the crystal plasticity model. What we always care about in these surrogate model types of situation is, can it actually reflect the more difficult time-consuming modeling? And it does. Comparing the dotted versus the solid lines here, it's able to match it really well. This is for the ML-VPSC. It's also able to match it really well for the ML-EVPSC. And another way to tell how good the model is working is to compare the actually evolved textures. So comparing them, we're able to see how well these things actually match. Here, for example, is comparison of ground truth of the VPSC's textures with their ML counterparts, showing pretty good agreement. And then they actually tested this on sort of complex parts. For example, here's an example of a truncated pyramid where they're comparing the two different approaches, seeing how well it matches. Here's another one, this time on a truncated cone, where they're able to see how well these things match. And they look pretty good. So it's great that the microstructure is reproducing what the crystal plasticity model says. But is it faster? Well, here they show that it's actually quite a bit faster. Using the two different models, you get two different speed ups. One of them is 3.3 times faster. The EVPSC model is actually 63 times faster. So a pretty huge improvement from the gang at Georgia Tech. Read all about it in the latest issue of IMMI.